Okay, hello again. Continuing the TsString saga. This is sort of where we left off. I just recalled that I'd had this function for a while and forgot that I had this function, and I invented two more functions, like left and right. These two functions, I forgot I had them, and I invented functions that do the same thing, but with a different name. But that's fine. First three, the same as left. It's the left three, right? And the last three is the same as the right three. If I run this, actually, well, previously, I got the same result, even though they were different functions. Now what I've done is I've put them together and just let one call another, like an alias. The implementation was slightly different, what amounts to the same thing. It allows me to show you something. Let me just replace temporarily the new implementation with the old, so that it comes out the same. I always had first and last for a single character, and then I thought, well, why not have another version that takes an argument and returns a string rather than a character. So that also allows me to extract the last character as a string. I put a 1 here, the last one calls this function. Okay, should be the same. See, it's the same. Now this one uses a macro called umin, which I don't know if anyone's ever written this macro before, but it's not what you would guess, a version of min that returns a uint. Obviously I'm assigning this an int, and there's no warning. What it is it's the min, same as min. We can see the definition there, where it takes the arguments to be unsigned. Okay. Now, so what's the big deal about that? The reason that that's a big deal, or can be a big deal, is that if I want to get, say, all of the first cars using this definition, all I have to do is say -1, and that should give me everything. I want the first -1. See? And that works because the minimum value of -1 as an unsigned character is a great big number. So the minimum of length and -1 in terms of uints is get length. Well, the return value is still an int, but the comparison is unsigned. Now, I don't know if that works with this. It should work with this too. Otherwise, maybe I'll just take the other. 1 minus cert. No, they both work that way. Don't get an assertion. No. Let's see now. Mid count. I thought I had an assert here. Oops, that's this one. Oh no, I'm allowing negative. I see. Okay, so either way it works. Works out the same, but in order to avoid any confusion, just make one set call the other set, and so you can see that they're the same thing. This reads pretty good. You know, first print the first 5 characters, right? Or print the last 2 characters, right? Now, last here is not a string. That's a char, just a character value. To make this a string, I'd have to say 1. Okay, so now cutting and doing things like that are all versions of mid. Upper and lower, I showed you vaguely, quoted, capitalized. Now the next thing to look at, well, one thing I should just mention, since it's another example of not reinventing the wheel, is, and I'm going to get to these comparisons too, is operator plus. That is not plus equals, but plus. Plus is a thing that doesn't modify the string, returns a new string, which is the sum of the string plus this, some other thing. So I could say, I could use that here. That uses plus. It's not going to modify with a temporary string created for this last 2, right? And it turns out that this plus won't modify that, even though we never get to see it. I could, I guess, make it. Still want that. Now this should invoke the member function plus of this, hopefully. Although this doesn't have to be declared or defined as a member, you can do it outside the class. And maybe I should have put them all outside. Just as like with logical font or something. You can always declare this type of operator outside of the scope of the class or struct. However, it is using the member version, and all that does here is invoke plus equals again. Now, that's one way to add things. Another way is to put something on the left. And if you want to be correct English-wise, we're going to put the word R on the other side. Now this cannot, obviously cannot invoke a member function of this because this is just a literal string. So it's got to go somewhere else. And where does it go? To a non-member function that takes a left-hand operand pointer to characters and the right-hand reference to a string, and again it just invokes the plus equals function. Similarly, adding two strings together is not a member of TsString. It's a global member which invokes operator plus, which in turn invokes plus equals. It all goes to plus equals, and so that covers addition. Okay, very quickly, one needs to compare strings against strings and against other things that one might compare a string with, and it's required in this case to have all of these comparisons defined because of the automatic conversion. We don't want, for instance, a string to get converted to a pointer type and then have a pointer comparison occur. We want these types of comparisons. Now, all these ones do are invoke these ones, and these are all member functions. There are two functions. This is not really needed, but this is another way of saying exactly equals. This is a way of saying equals, but ignoring case. These are partial comparisons. Compare the first so many head equals. This is like this string stir here's a true statement, or a true something that will return true. I don't know if I got my macro idea. Stir, the head of stir is equal to this word hello. Okay, so this should print out it is true. And it does. So this should return false because that's a case-sensitive comparison. False. But if I put an I here, that makes it case-insensitive, and it will become true again. Okay. However, now the question is this true? And it should be. I hope so. This is the checking the off by one. It is true. But if I add a space here, that's got to return false. And that's false. A thing which is of one length cannot have its head section be equal to something that's longer than itself. Head equals is a partial comparison, of a string with a smaller string. So just another thing. It's something that comes up quite a lot. Head equals, for instance, path comparison. So you might want to compare two path variables, path names, and see if they both are in the same subdirectory. And one way would be to ask if the head part of the full path is equal to the subdirectory. If it's a path, right? One might be curious to know if this is in the temp directory. Right? If this string, if its head starts out with C temp, then I know that it's in the temp C temp somewhere under C temp. That comparison. Now there are a few more aliases that exist. Some obvious things. Is empty means that it has no data, right? Is null means that the pointer itself is null, or the length is equal to 0. Length equals 0 it's probably enough, actually. But I have this here for some reason. When this is null, this is 0. So in fact, this first test is irrelevant. Get length is just an integer version of len being a size t, and that's useful in cases where you have an integer and you want to compare. You want to do a comparison, and you don't want to have a warning, and you don't want to, and you're tired of casting things. You use this one. Is blank. No, I'm not sure. I might have changed this to blank space instead of white space. Anyway, is blank means there's no visible characters. A to L converts a string to long. A long. It also handles arithmetic expressions. That's a long. This is a long explanation that goes through the evaluation part, but the idea, I'm sure, is familiar. Now I just want to get to searching and finding things. Okay, because that's the real. Well, okay. Just quickly let me mention what these things do. Remove here removes any occurrence it finds in the string of this particular character passed in. All right, and you can imagine what that code looks like. If it's empty, we don't do anything. At the start of this function, I take note of where we started and take note of where the ending position of the string initially is and how many characters we have removed. Now, I don't know what this warning is, but it comes up. So now this beginning thing gets modified. I'm searching for, from the beginning, that character that I don't want. If I find it, I increment, take note of the fact that I removed something, and now this is a memory move from the point I found where I found the character, sorry, +1, to where I found the character. So this is a downward move from some position along the string. The remainder of the string moves down 1. And that wipes out the one I just found. And I just continue that process, now starting from the new beginning, which no longer contains that character. Try to find the next. And at the end of the day, this will either be 0 or something. If it is non-zero, I'm using that setLength function to simply set the value of m_length and return the string. So this doesn't actually do any reallocating, I don't think. Or it does. It does do a resize. It doesn't have to, but it does. This string class is not designed for optimization. It's designed, perhaps one could put in optimizations later on, but I tried to make it such that anything that's off by a single character will turn into a bug, so that no bugs are hidden. Everything is exactly one character away from being wrong. So everything has to be exactly correct for it to work correctly. And so far everything seems fine, although new bugs do come up. Condense is like remove. Now, condense, though, doesn't remove all of these characters. What it does is it removes consecutive occurrences of a character and changes it to them to single occurrences. Just give you an example. This can I use regular? Yeah. Here's a string with some spaces. Okay. Now, suppose I have a string like this, and what I want to do is I don't want to get rid of the spaces, but I want to make it just one space. You know, I only have that this space is, and so on. Then I can condense, and it takes a character value, and it modifies the string, and it returns a reference to the string, so I can just print this out as is, and you'll see what I get. Okay, so it took all of the spaces and condensed them down to 1. Now, this sort of thing is actually very useful, especially in the case of paths. You'll notice that sometimes in path variables, you'll end up sometimes with correct number of slashes, sometimes the wrong number of slashes, because things get appended and whatnot. If you're given a path variable, you can do what I would do. Sometimes there's forward slashes too, but if you only had backslashes, I don't want to have double backslashes in the path. That usually indicates an error. That could occur at the beginning, but assuming that it's not the case, I want this to just have single slashes, and there it is. If I didn't do that, then you can see I'll have 2 here and 2 here, and that's not correct. This winds up happening when people are when one is writing a function and adding extra bits to a path. Sometimes the thing already ended with a slash, and you add an extra slash, and so on and so forth. And that typically the forward slashes can occur, but I want all this normalized, right? Something like this. I have a replace function, and what I do typically is I replace forward slashes with backslashes, and then I condense the backslashes, and that normalizes it. So I have a mess like this, but what I end up with, whoops, okay, this only takes a single character. This takes strings and one takes character. That normalizes the slashes, and that helps with comparisons. Okay, let's see. I just want to give you a quick intro to the most important part. The most important thing to do with any kind of string class, somehow not emphasized in other string classes, so as much as I want to emphasize it, what you typically are going to be doing with strings is searching for substrings, right? And either replacing substrings or parsing or whatever, right? The whole thing about parsing is finding and possibly replacing things. So therefore, there are a bunch of find functions. Really, there are only 2 functions here. There's one that takes a substring, right? And here's another that takes a substring. One is case sensitive, one is case insensitive, and these take single characters, but all they do is this same trick. Okay? So this calls this, and this calls this. So there are only 2 functions here, and they're the same idea. Count counts the number of occurrences of a substring. Account insensitively does the insensitive thing. Find a word is defined to be something like whole word search in Notepad, right? A substring match, but that's not part of a word. So this is a whole word search. This is an insensitive whole word search. This is the count version of that. Now those are for specific substrings, and the way that they work. Are well, first off, there's for each of these there's an internal one that you don't see, called find, which does the job of searching for something. using some other function, usually something from the C runtime, to do the search part. In this case, there's a function called find, the same idea, which is implemented using this search function. Okay. However, this find is the same find function that uses this runtime library function for its search. That allows me to not have to rewrite this function. So there's a lot of grouping of functions by making this replaceable part, making the searching replaceable part. Similarly, with the word search, now this one is something that works with this find here, one of these or the other of these finds, which are member functions, and those member functions, as you saw, have their replaceable part. And so again, grouping things together, I don't have to reinvent the wheel. I have a thing that finds some substrings, right? And I can turn that into something that finds words by using this function, and this function uses either this or this, and so there's not that much code to do the searching. Same with count. So in the header here, there are a few things that look like a complicated mess, but in fact there's not much to it. These are locators. I call this a locator. It finds a position in a string of something, and this is a member function. This is a type of comparison member function. It returns a Boolean value, or if true or false, depending on whether this object is equal to the thing passed in. These are non-member functions. Here's one for comparison of two strings. Here's one for comparison of two strings up to a given length. Here's one for locating a pointer to a substring, where this is turns out this is the substring part, and this is the string part. So we got some member type things and some non-member type things, and these are the functions that you never use yourself, but that use those locators, those locator functions. And this is an example of some functions that use the comparison replaceable part. Now, I'm not going to go through all the details, but I can show you an example anyway. Here is the implementation of find. This is the implementation of find for all of the find functions. All the functions that have the name find, right, used by this class. This part is an unknown. It depends on the kind of search. And it locates a pointer to a substring in a string. And the way this function works is it finds a pointer using the locator provided and its string plus some offset, and the substring provided here. Okay, now that's not a complicated function. It's actually really 2 lines long, and it covers all of the finding for all of the cases that are covered in that list. And this is the word find, okay, which also uses a locator. The locator is a member function, unknown, passed in value. Now it uses some extra logic here to determine if it's a word or not. In the case where a substring match is found, if this condition, this has to do with whether or not it's a whole word or not, if this condition all ends up being true, then that position is returned. Otherwise, it continues searching for the next substring in the string that might match using the locator function provided. Now, again, I'm not going to explain this part. You can look these functions up and see what it's doing. This is one way to determine if something is a whole word. It may not be perfect. I should be using probably the locale versions, to include European and such. But that's how I have it. Count, again, similar idea. There's one function that does counting the thing, and it counts substrings. The locator is something provided. Now, this should also work for count word. There shouldn't be a special function for count word, because I can use the find word locator, right, and use this count with that replaceable part. See, here's count word. So it's count word start, and here's the replaceable part, the thing that finds words. If I want to count things not by word, but just any substring, I use this kind of find. So all these functions are just one-line functions, and all of the work you saw. That's the entirety of it, but it's, there's more than one function involved, because all of these things have a replaceable bit. Now, once you're able to do that, and it took a while to get all this right, then it becomes a very trivial matter to start doing parsing of strings, and search, replace, and so on. If I want to replace one word with another, I can easily write those functions in one or two lines. And as far as the rest goes, that's about it. These are some special functions. This is a thing that builds a binary string from a given type. Okay, now all that does is, if this is T is a D word, let's say, it goes through and pulls off, one bit at a time, and builds a string made of ones or zeros. Okay. Here it's and then that's a space. Here it's taking 1 to the power of some bit and checking to see if that bit exists in the thing provided. If it is, it adds a 1 to the string, otherwise a 0. Here's a thing that does that prints numbers with commas, for 1,000 separators. And then lastly, there are these variable argument list type things, and a thing which appends using a format specifier and a variable argument list thing, and that is used for these streamy operators to allow me to use these, the fancy stuff that you get in IOStream, that kind of thing. If you love C out and C in, you can do that. I could do for anything that's defined as a member here, like float. I'll put S. And start out with any, I could say stir 1.3F. Now that's float, right? But I have a function that takes a float and a reference to a string, and it appends to the string using this appendf, which is essentially like, see, all this appendf does is call like stir, what's that? Stir, gosh darn it, the runtime library thing. Won't have me. Eventually we'll get to it. Here, vs printf. This is a function in the runtime library which prints, does like a printf but to a string instead of to the console, and this is what it's called. You can use the same function to find out how big a string you need in order for it to complete its print, and then you can allocate a string of the correct size, and that's all these do. And these things can be compounded. For instance, I could add a string here. Okay, now I realize that this isn't, quite as pretty as putting a C out here, right? But it really wouldn't be very difficult to create a struct that has an arrow operator and that calls put S. Alright? I suppose a struct my out. This could be void, but let's make it int. Who cares? Sounds good. Default constructor. I don't think I need one. How about I make a I define one. Yeah? Now, I'm just making this up, but I don't see any reason why it shouldn't work. It has an operator. I'm using the operator. I have a string thing operator that does that. So I probably need a string first. But we can probably sort that out. So that I don't have to write this. Shouldn't be that hard. Oh yeah, it could derive from string. Come on, compile. Okay. Now, okay. Now, it's true I had to put brackets here, but IOStream, in order to well, they call this CF. Now, in order to use IOStream, I have to include about 1,000 more header files, a completely different lib. If it's a DLL version, I have to ship another DLL with my program. The C++ part, and so on and so forth. But really, this is almost exactly what it amounts to, right? It's just a function call. This thing prints. There's nothing special about IOStream. It's just a weird way of saying put s. Alright, anyway. So that's enough for TsString. You have the header file and everything. If you just ask me, and you can examine how all these things work. And I would suggest that you download the code, step through it, especially this string class, because it's a very simple, straightforward string class. No magical anything, and you'll learn. I think you'll learn more from stepping through it than just seeing that this is magic. Stepping through it is not magic. If you F8 into this, you're going to see it's going to go into these functions, which is going to go here, which is going to go there, and it's not very complicated. Okay, now that's good for my TsString reference. It's finished. Well, maybe I'll add more later, but that's the basics. The searching, again, stepping through it is the way to see it, not by looking at the code. Do a word search and watch how everything falls together. It's very simple. Okay, now back to my. I don't know I know what I'm doing actually. I have a few things I want to do with my magic notepad. Like one of the things I added is this Control D, something I always wanted in the real notepad, and now I have it in mine. And there's other things that I want in this notepad, and I can easily implement, like tab does that, right? But what I want it to do is what it does in here. Do an indentation. Easy to implement, and also I can fix the search replace. I know how to do that now. without it taking 2 hours. It can be done behind the scenes without any updating of the screen. A few things like that. Okay, see you.